First, I want to say that it's really nice to be here at this NAIC conference again, and especially last night's dinner was really cool. The setting was fantastic, and then having it there with the big submarine and everything. And the food was also excellent, of course. But I especially like the setting, and it's been a nice conference, and I slightly tuned my slides after a dinner discussion on Monday, so I realized that maybe we need a bit more introduction to quantum computing than I had originally planned. But let's see, if I start by asking the audience, how many of you have run a calculation on a quantum computer? Okay, so then I think it's good to have a few more introductory slides. So I'll start by defining what a quantum computer is. So a quantum computer is a device that directly exploits some quantum mechanical phenomena in order to perform a calculation. And these quantum mechanical phenomena, so they are superposition, entanglement, interference, wave function phase, and so forth. But is there a pointer here? Okay, it's like this. Cool. I want to highlight there the directly, because as many of you in the audience know, so quantum mechanical effects are already affecting standard GPUs and CPUs, because the scale of the smallest components has just become so small that we are already in the quantum regime of the very small already on standard processors, but there's just a nuisance and the source of noise and problems. So one actually wouldn't want to have the quantum effects in normal classical processing units. But here with the quantum computers, the idea is to really use these for something useful. And the reason for this is that by doing this, one can really devise some extremely powerful solutions to certain types of problems, modeling problems, and by this really enable completely new science. So that's maybe the main motivation, and why also 40 years ago quantum computers were invented as a thought experiment by Feynman and Deutsch and others. But I also want to directly point out what a quantum computer is not. So it's not a super fast version of a standard computer. It's completely different. So it's not something that will just suddenly run all your calculations 1 million times faster just because you're running it in a quantum computer. So it's a very different device, and just for example, programming quantum computers is completely different at the basic level from programming classical computers. So if you think of what a classical computer actually does when it performs a calculation, so, well, we know that all the information there is represented by bit strings 1 or 0, and always when a computer does something, all that happens inside the machine or the memory or wherever is that these values change. So 1s become 0s and 0s become 1s. So a computer program is actually just a recipe for which bits to flip and when to do it. That's really at the basic level all that happens. And then of course there's a humongous amount of these bit flips taking place in order to do something useful. But really if you look at the basic components, that's all that happens. It's just flipping between 1 and 0. So how could this be improved? Well, paraphrasing an English writer, to be and not to be, that's the answer. That's where we come into qubits. So a quantum computer, instead of bits, uses quantum bits shortened to qubits. And these can be 1 and 0 and everything in between at the same time. This many of you probably have heard. But this means that these, the basic information units are much more powerful in a quantum computer and much more versatile than standard bits. And the state of a qubit can be described as a point on a sphere. Okay, well, it's difficult without a pointer, but well, we can think of this sphere as the globe. So the value of 1 qubit is somewhere on the surface of Earth. And a classical bit, on the other hand, so can only have 2 values, 0 or 1, so it can be either at the North Pole or the South Pole. Okay, this also shows that a qubit is much more powerful than just a bit, because we can see that we can have much more information just in one qubit in principle during the calculation. But it also means, and maybe shows also directly, how programming a quantum computer becomes much more complex. Because now you need to do much more than just flip between 0 and 1. That was the basic operation principle of a classical computer. So, okay, one both can, maybe it comes up, one both can and have to take advantage of this added flexibility in order to get some advantage from a quantum computer. And in addition to just moving around the state of the qubit on this sphere, we also have to then use these other effects like entanglement and wave function phase and so forth. So just to drive home the point, so usually this figure that illustrates the state of one qubit is called a Bloch sphere, and as said, so we can think of this as Earth. So there's a small video here. So this is now a qubit, and the state of the qubit can then be any point on this sphere. So it can, for example, be on the North Pole, and then it would be 0. And then the idea is to, when you program the computer, is to move the state of the qubit somewhere. And if we would have a classical computer, all we could do would be to jump from the North Pole to the South Pole. But now, because this is a qubit, we can do much more. So we can go from the South Pole, for example, to the equator. And this is, of course, an operation that you cannot do with a classical bit. But then you actually have now a 50-50 superposition of both 0 and 1. But you can also go anywhere else on this. So you can come and visit us in Espoo at CSC. That's another point on the surface. Or then you can go to the other side of the world and visit Sydney. And all of these small movements is something that you have to take care of. And it's not just jumping from one side. You also have to be able to do these very precise small adjustments of the position of the state of the qubit. So this maybe illustrates a bit both the added power of a qubit compared to a bit, but also especially the added complexity of programming them and getting something useful out of it. So when we have these qubits in this superposition, it's called, when you have it as both 0 and 1, or some portion of state 0 and state 1, it means that all these inputs can be processed at one time. We'll show it a bit later in maybe more explanatory, but the difference here to a classical computer is that in a classical computer, the inputs need to be computed one by one. But in principle, in a quantum computer, you can make a superposition of all the inputs and then process them all at once. But at the same time, we should remember directly that the quantum computer only gives one answer. So even if you would be able to feed it with lots of input in superposition at one go, you always only get out one answer in the end. So in general, this means that quantum computers are suitable for problems where one is interested in the best answer. So let's say we have 4 playing cards there, and we want to figure out where is the king of diamonds. And that's a rather easy or a typical task for a quantum computer, because then we can feed all these 4 unknown cards into the quantum computer at once, and then it will tell us that the king of diamonds was the 4th card. But if we actually want to know what all the cards are, so we also want to know where all the different 9s are, then that's not a problem for a quantum computer, because then you actually have to do it 4 times. And that's a classical problem. So if you want to know the position of all the cards, then that's a completely different type of problem. Then you're not finding one answer out of many. These types of problems then are not suitable for quantum computers. Then you really have to use classical computers. So in a bit more detail, so if you now have a simple algorithm that takes as input 2 bits, so there's then 4 options. On a classical computer, 0, 0, 0, 1, 1, 0, and 1, 1. And in a classical computer, if you want to answer for that, you have to run it 4 times. And that, of course, scales exponentially. So if you have 3 bits, then you have to run it 8 times. And if you have 20 bits, then there's a million different inputs, and you have to run it a million times. But a quantum computer, what you do is that you prepare this superposition of 0, 0, 0, 1, 1, 0, and 1, 1. So now there's an equal probability of all of these, so to say. And then you feed in this to just one calculation in the quantum computer. And out you get then the answer, but during the calculation, we can see that this, okay, this doesn't really work. These are supposed to show the probability wave of this state. So we can see that they are equal here. But in the end, the idea is that during this calculation, you don't only compute the actual result of the calculation, you also at the same time have to take care of this wave function interference and destructive and constructive interference in order to increase the probability of measuring the correct answer. Because it will calculate the answer to all of these inputs, but that's useless if you just get out then randomly one of the answers, because you are looking for what is the best one, and now we are assuming that the best answer here is the 0, 1 function. So during the calculation, you also have to take care of increasing the probability of measuring the correct one, which is that one. So that adds another layer of complexity. So again, we cannot go into details in this short one, but it just shows that programming quantum computers is much more complex. Okay, and then what does actually a qubit look like? Qubit is any system that can be in this superposition of two states, and we denote those states 0 and 1 with this bracket notation around them. So one maybe easy example to understand is the ground unexcited state of an atom or ion or molecule or whatever. So we have there an atom that has this one blue electron in a very simplistic Bohr model circling around the nucleus at the innermost orbital. And this is then the ground state because, well, the positive and negative charges want to be as close as they are allowed quantum mechanically. But then we can shine light on this electron or the atom system as whole. And if the light is of the correct frequency and we have the correct time there for actually to excite it, so it needs some energy, the electron or the system captures that energy and the electron is moved to an outer orbit, which is now the excited state. So this is actually a good system where you can have two states, 0 and 1, and something like this could be used for classical computing as well, because this could be a bit as well if you just have 0 and 1 there. But now we have a quantum computer, so we want to create this superposition, and so we can see what happens if we only use half of the time required to feed enough energy to this system. Well, due to the laws of quantum mechanics, what happens is that the electron both moves and doesn't move to the upper orbit. So in classical mechanics, if you just give half of the required energy, then nothing happens. But because it's quantum mechanics and we are at the microscopic level, then we get this uncertainty, and actually what we end up with is that the electron both jumps to state 1 and stays on state 0. So now we have a superposition of 0 and 1, and this is our information unit, our qubit now in a 50-50 superposition of 0 and 1. Okay, I also put here another video I found of how a quantum computer actually works. This is an ion trap quantum computer by Quantinuum, and they made this nice video of how one moves around the qubits, because when you're programming the qubits, then you will also want to do operations where these two qubits interact, and that means that they somehow have to be close to each other. And in this ion trap computer, so one actually moves around the qubits physically so that they come then in close proximity with each other. And so this is of course also something that doesn't happen in a CPU, so you're not moving the transistors around there physically. But in this ion trap quantum computer type, for example, then you do this, and you have to do it so that the qubits can interact with each other. Okay, and then to the question, what can one do with a quantum computer? And this came up on Monday during dinner, that will it run Doom, this first-person shooter game that is now 30 years old. And then I, of course, said, no, it will not run Doom. This is not something that the quantum computer is good for. But then I thought, okay, I should probably check this, just so that I don't say something stupid here. And actually, No, it doesn't run Doom. This is a pregnancy test. But maybe one takeaway message from this is that a pregnancy test is more powerful than a quantum computer for running Doom. So we have to find something else to do with quantum computers than play first-person shooters. This problem is often brought up as a typical example of where we have a rather small number of input parameters, but which leads to a very complex problem, and we are only interested in the best solution. So the traveling salesperson problem, that find an optimal route that connects a set of endpoints. And if you just do this in a brute force way, then there's actually a factorial number of options. So already we have 4 cities, then we have 3 factorial different ways of connecting these points. So that means 1 times 2 times 3, so it's 6 options, and that's something that you can do easily on pen and paper, and you can check it out yourself. But this problem really blows up. So if you have, then if you had 5 cities, then it would be 1 times 2 times 3 times 4, so it would be 24 options that you can still do with pen and paper, even if it becomes quite cumbersome. But already when you have 10 cities, then there's over 300,000 options, and if you have 20 cities, there's 121 quadrillion options, different options of connecting these points. It sounds almost unbelievable that how can this problem blow up like this, but it doesn't. You can test it out with the lower numbers. While the 4 cities is doable with pen and paper, the 10 cities, no one will do that by pen and paper. You need a computer, but with 20 cities already this becomes a problem for even the largest supercomputers just to solve in a brute force way. But here we are not interested in all of these options. What we want from this problem, the whole idea of solving this problem is just find the best solution. So one solution out of this, for example, 121 quadrillion. So this is a typical problem where quantum computers are thought to really do well. It's also a typical misconception that quantum computers would be good at this. They are not for this either. This is a good demonstration of the type of problem. But actually for this one, there exists very efficient classical solutions also to the traveling salesperson problem. Because, of course, not all the classical good algorithms don't go through all of the options. There are other ways to do it. For example, by simulated annealing. So this is just a demonstration of how one rather quickly gets a rather good answer for connecting some large cities across the Earth. Actually, the record for solving this type of problem is by connecting star maps with over 1 billion stars. And one has been able to calculate the shortest route between these 1 billion stars with a maximum error of 4% on classical machines. So we should remember that this illustrates also this, that when one is trying to use a quantum computer for something, one needs to be aware of what is the best solutions on classical machines, and not only compared to the brute force worst way of doing things. HPC has, of course, been developed now for decades, and classical computers are very efficient at many problems. But then there's another optimization problem that is not the traveling salesman problem. There's lots of these that actually are also optimization problems that do not have efficient classical solutions. And one of these is the electronic structure of molecules and materials. So how to know how the electrons interact with each other in order to make up the properties of any molecule, any material, any drug molecule or solar panel or whatever. So this is a highly complex quantum mechanical problem. And for this type, even if there are some good approximations that you run, the computational chemists in the audience know that there are solutions, classical approximations to solving this problem, but they do not work in all cases. So when you have a very complex electronic structure, then also the supercomputers start to choke. But this is a type of problem where quantum computers are perfect, because it's a quantum mechanical problem that you solve with a quantum computer, and and this is also the original idea why one started to think of the idea of having a quantum computer. So, and this is of course a huge problem in itself. or popular problem before AI took over all the capacity of the machine. So, well, at CSC, so now roughly half of the cycles are used for AI. But before that boom came a couple of years ago, half of the CPU cycles was used to solve the electronic structure problem, and it's still a major part of supercomputers around the world. So speeding up this will have a major impact. So this was already mentioned a bit in passing, but quantum computers or quantum computing is good with problems that have a moderate amount of both input and output data. But then the idea is that the relation between input and output should be a very complex equation, a high-dimensional problem, so that it's very difficult to solve it on classical computers, and then you hope that you have a quantum algorithm that would do it much more efficiently. So quantum computers excel at problems with a large potential solution space, so to say, like the traveling salesman problem, except that that's a bad example, except that it's illustrative. But that types of problems. So what this figure is trying to say here is that the number of input data to a quantum computer has to be quite small, on the order of the number of qubits that you have there. But then with this small data, then finding out the solution to whatever problem you have should be a very difficult equation. Like, for example, the electronic structure that in principle scales exponentially if you want to solve it. The Schrödinger equation or the Dirac equation perfectly. And then in the end you want only some limited number of results. So for example, in the electronic structure problem, where do the electrons like to be around these atoms? So some typical HPC QC applications in the near term. I didn't say it explicitly here, but it should be implicit now that quantum computers will not replace supercomputers because there's so many things that we need to have supercomputers for always. So quantum computers will never replace classical processing. It will augment it by providing solutions like a coprocessor, accelerator for certain types of problems. But the electronic structure problem was mentioned, optimization problems in general, and here we have to also remember that we don't need to be mathematically completely accurate here, because if you're looking at some sort of larger problem, then if the solution is good enough, well, then it is good enough. So in any optimization problem, you can rather easily check, is this a good solution? And if a quantum computer in any optimization problems gives a better solution than a classical computer, then that's already useful. It doesn't have to be the globally best solution to anything, but as long as it's better than you could do before, then you actually win. Machine learning is another field. I will not go into that more here now. But I want to mention financial applications and insurance applications. And in general, financial houses are the first to jump on any new computer technology. And that's true also for quantum computing. So there's lots of activity in and even public articles published by big banks around the world where one tries to find out quantum algorithms for this and that problem. And the reason here is that in this application field, you don't need to be 1,000,000 times faster. You don't need to be even 10 times faster. If you're 1% faster or more accurate in whatever you're doing, some risk analysis or portfolio optimization, then you get lots of money. So even small incremental advantages in this sector are worth lots of money, and that's the reason why one also looks into this properly already now. But from the scientific point of view, then that might not be so interesting except in general algorithm development. But we have to remember that there's not only scientists using HPC systems now either. It's marketing and whatnot. So what is needed for quantum advantage, which means that the quantum computer should do something that you could not do without it? Well, one thing is that you really need a deep understanding of the problem that you're trying to solve. And here the traveling salesman problem is again good. That's something that has been studied for a long time. It's been a rather nice thought experiment, and good for mathematicians to figure out how to solve it efficiently. These classical modeling algorithms have been developed now for 100 years for computers, and so there is a large head start in developing efficient classical approximations to something. And if we want to do something with a quantum computer, then we need to also include this knowledge. So we need to know what the actual bottlenecks in any sort of modeling workflow is, and then concentrate the efforts on that one. So for this, we of course then also need a deep understanding of the possible quantum solution at hand. So we really need to combine all of these different knowledges. And then we have to know how to exploit classical support software, as I put it in there, because quantum computers at this stage, so they really need lots of support by HPC systems in pre- and post-processing of the data, compiling and transpiling quantum algorithms, for example, even machine learning for creating the quantum algorithm in the first place is now gaining traction. So one is using large language models just to program the quantum computers and outsource that because it's just so difficult for many reasons, as slightly were mentioned here already. And error mitigation and all sorts of this. But in order to be able to do this, we really need, or the users need access to infrastructure, HPC-QC infrastructure. So, and the reason here is that quantum computers are different. They are completely different from classical supercomputers, but they're also different from each other. And this means that in order to actually start developing the software needed, both the classical software and the quantum algorithm, then the users need to have somewhere to test this out and see how it works. So users need really access to several different quantum computers. And I just want to mention here, Nordic Quest, it's been come up already during this conference, but this is one of the projects that tries to facilitate access for users for quantum computers. And I will not dwell on this more because it was already presented, but it's of course apt for this conference to highlight it. But the idea is anyway that we need to have lots of efforts for bringing quantum computing out to the users that can potentially use it. Okay, so the first question was, what can one do with the quantum computer? So now it's time for when can one do with the quantum computer? And here we can note that quantum computers are actually already faster than classical supercomputers. So they can do calculations that supercomputers cannot do. But the problem here is that due to noise and imprecise control, noise means that outside sources like temperature, electromagnetic radiation, whatever, affects the calculation and makes the quantum state disappear. And also this imprecise control refers to how precisely can we control the state when we move the state of the qubit around the sphere there. And this is still, well, it's, well, if you put it nicely, so it's not in any sort of optimal condition, but actually quantum computers are really just starting to solve these problems. But this means that quantum computers crash almost immediately. So, which means that there's actually not time to do any useful calculation before the computer has crashed. So if you have this car analogy, so then we can compare this like quantum computers would be the fastest racing cars that anyone has ever even dreamt of or built. And they go super fast. But the problem is that the batteries run out after 1 or 2 meters. And if you're in a Formula 1 Grand Prix, then even if you have a car that goes 10,000 kilometers per hour, but it stops after 2 meters, then it's useless. But still, the potential is there. So it did go 10,000 kilometers per hour for a short while. And also, well, the steering, if you just turn the wheel 1 or 2 times, then the steering wheel falls off, which is also a problem. But all of these are engineering problems, and they can be solved. And I just want to say here that there's no foreseeable roadblock that is blocking this progress. It's just that this is a very new technology, and that's something that we need to remember. We are just starting to see the first semi-useful quantum computers, and there's lots of these small things that needs to be taken care of. So when can we expect to have this? And well, that depends on the definition of quantum advantage. The usual one is this wall-time quantum advantage. Number one, I marked it here, which means that quantum computers help solve problems faster than one could do with if I would use just classical binary computers alone. And this is still some time away. It needs massive development, both on hardware side, but also on the algorithm and software side. So we are not there yet. But the other one that is being noted more and more now is so-called green quantum advantage. And this means that by using a quantum computer, it would lead to a higher solved problems per watt or science per watt ratio. So this means that the QPU, the quantum processing unit, doesn't need to outperform HPC in speed, but if it, let's say it does the same computation 10 times slower, but using 1,000th of the energy, then that's for many problems, that's very useful. Then the other one I put here, quantum quality advantage, which is a bit more difficult to define maybe, but that would mean that quantum computers provide somehow more accurate or better quality predictions for some problem. And this comes from the fact that when you actually want to use a quantum computer to solve a problem, you have to solve it in a completely different way than you would do with a classical computer. Because you cannot just recompile a classical program to a quantum program because they operate at a completely different basic level with the qubit and bit operations. So it means that you really have to rethink what am I trying to solve and then do it in a different way than what you are doing presently with HPC systems. And through this, one can then come up with solutions that actually, just by solving a problem differently, you get better results. I'll come back to the number four. I have separate slides on that, but call it here quantum control advantage. And all the rest we can then put in other quantum advantage. I just want to mention here that, of course, it is an advantage if you as a researcher get funding, and there's now lots of funding thrown around for developing quantum computing. So that's an advantage for industry. The advantage at this point is to really create early IP for solutions using quantum computers that do not yet exist, but will come after some time. And of course, one should never underestimate the value of PR either. When a company is doing something with the latest high tech, it is seen as a modern company. And well, at least at this point, it's also seen as an advantage for meddling with quantum computing, just for the sake of meddling with quantum computing. So here I just put a timeline, but I want to emphasize that this quantum advantage is actually something that we have already now, both for category 4 and 5, and the others come a bit later. On purpose not put in what this unit of time here is. It depends on your level of optimism or pessimism or realism. But to return to this number 4, this quantum control advantage, we should also think of what is a quantum computer also, instead of just a machine that performs calculations. It is actually a high-precision quantum laboratory. And this comes a bit of a side effect of building the quantum computers, because in order to have quantum computers perform the calculations, you really have to have very precise control of the quantum world, of the quantum states of the qubits there. And as a side product, then, you actually have created something, a laboratory for physics that didn't exist before. So just by having to tame the quantum world to perform some computing tricks, you have at the same time really managed to take hold of how does it work. And here we come to these non-computing applications, which means that you're actually not solving a mathematical equation. You don't want to use the computer to calculate something directly. So instead of using the computer to solve some algorithms, we use their capacity to really have this fine control of manipulating these quantum states. And I just put some examples here of what one used this for. So on quantum computers, one has, for example, created these time crystals, which is a new phase of matter, where a normal crystal is like salt, where you have sodium and chloride atoms in a repeating pattern in space. So time crystal is something where the pattern repeats in time instead, without losing energy. So, for example, the qubit configurations can flip between different patterns continuously throughout time, in principle forever. Of course, in practice, not. But it's a new type of, new phase of matter. Another example, a recent example, is this, that physicists claimed at least to create a type of wormhole on a quantum computer. And also black holes as such have been created on the quantum computer. Another one here from late last year was one also used quantum computers to slow down a chemical reaction by a factor of 100 billion. For the chemist here, so it was a conical intersection, which is difficult to treat with classical computers. But here I could then really follow what happens in that chemical reaction, because just because one did it on a quantum computer, the time scale is completely different and one has time to observe what is happening. And the interesting part about this, at least for me, is that this really blurs the distinction between an experiment and a simulation. Because, of course, you can simulate time crystals or wormholes or black holes on an HPC system. But what you're doing then is just solving mathematical equations. When you run something on your laptop or HPC system, you're not creating new phases of matter. You're not creating black holes. You're not creating actual wormholes. But when you do this on a quantum computer, you actually, while you are studying whatever phenomena you're studying, you are in a way creating that physical state. So you are actually creating a sort of a black hole. You're creating a sort of a wormhole on the quantum processing unit, while you are at the same time studying how it evolves and what happens. And I think this is, well, it sounds like science fiction, but it is something that is being done, and it's something that one could not do before quantum computers existed, because one didn't have these high-precision laboratories where one could suddenly create a black hole on the computer chip. And I want to emphasize that one is not simulating now just the black hole. One is not solving the equations of how would a black hole, according to these equations, behave. One creates that black hole and looks at it, what is happening. So this also brings a completely new user base to HPC systems. These experimentalists that actually want to use HPC services for performing experiments. Because also for these experiments, all this HPC pre- and post-processing is highly useful and even necessary to really filter out the noise and preparing the states and so forth. So we should look at all of this as a really synergistic ecosystem where you combine the best parts of HPC and quantum computing, but also increasingly machine learning and AI. Because we are going to need, or at least it will be very beneficial to use AI for supporting quantum computing. So I'm not now talking about quantum machine learning. I'm talking about using classical machine learning and AI to enhance the performance of quantum computers. So I just put some added values there. So, for example, compiling a quantum program, transpilation is lower level compilation, qubit routing is even lower level. But anyway, creating this program, the circuit, the set of logical gates that you want to run on a quantum computer becomes a highly complex optimization problem, especially when you have more qubits. Because as mentioned, so the problem with quantum computers is that they crash very fast. So if your program is too long, it wants to do too many operations that take too long time, then it will not finish before, you will not get an answer out of there before the computer has crashed. So it becomes very, very important to somehow compress the stuff that you want to do to be as short as possible. And this becomes a highly problematic problem when you have, let's say, 1,000 qubits or 10,000 qubits or 100,000 qubits or whatever. And I already mentioned this using large language models for creating the quantum algorithms in the first place. And the post-processing error mitigation, signal-to-noise ratio enhancement, and so forth. So I don't have time to go into more details here, but this is, as I see it, the future of getting the most out of quantum computer. We need to combine all of these fields. And I want to emphasize again that doing the actual quantum algorithms themselves is only a small part of this whole software ecosystem. So there's lots of classical programming that has to be done. So there's people who know classical programming have lots to give to quantum computing, even if they would know nothing about qubits. So in conclusion, well, we already have quantum computers that can outperform the best supercomputers, but not really for anything useful, at least on the computation side. Physics experiments is different. Their quantum computers already provide scientists with tools that did not exist before. But we need to develop algorithms that are short enough so that they complete before the quantum computer crashes. And this, as mentioned, is really a multidisciplinary problem because we need to combine the knowledge of all sorts of fields and especially remembering the application fields itself. So we need to have those that understand the problem at the deep level, both what is it one wants to solve and also how is it being solved now on classical HPC, and what is the actual problem. And it's not enough to just build better and larger quantum computers. We really need to have the software to run on them, and that's a work that has really just started. So quantum computing really is something of a dream come true for method developers because there's plenty of new areas to explore. It's in such a beginning that there's really lots of stuff to do. My background is in computational chemistry, so I can compare this to 100 years ago when Heitler and London started their first models, or Hartree-Fock came up with the first approximations to something. It is really starting now. So for those that are interested in doing this, there's lots of these, if not very low-hanging fruit, then at least if you are good, you can pick them, and there's lots of things that no one just had time to start even looking at. So it's not in any way an exhausted field where you have to really figure out what science should I do, so that it's not something that 45 different research groups are doing already. There's lots to be done here. And at some point, these quantum computers will transform from being a subject of research to really being a tool for research. And we are already at that breaking point for some applications. But then I just want to finish with this grand note that only by pooling and sharing resources and know-how can these grand challenges be tackled. And I think especially for this providing these services to users, the Nordic West NAIC project has been a really major example of how by cooperation one really can be more than the sum of the parts. So still I want to add one slide yesterday still on this. There was not that many of you in the audience who had done anything on a real quantum computer, but now today you actually have the chance. So there's the workshop on quantum computing today at 1 o'clock after lunch. And there the Nordic West infrastructure will be used to access a real quantum computer to do real and run real quantum algorithms. For example, you can be a Nobel Prize-worthy experimenter, so you will create these entangled pairs that, well, got the Nobel Prize in 2022 for 3 guys, but now you can do it in the hall next to this one, sitting down on a chair. And I think it's actually really cool that now anyone can do Nobel Prize-worthy experiments, either from the lecture hall or from the sofa at home. And this is enabled by having infrastructures like this. So if you want to take part in this and do it hands-on yourself, you need to get a user account, and that you get by emailing Jake Muff right now, or at least before 1 o'clock, so he can just set you up for the project. And it's in this room, right, Jake? Yes. And this QR code, it's the first time I created a QR code. I'm very proud of myself. leads to the web page of the workshop where you can also see what's happening. And I have 3 seconds left, so thank you.
Anyway, if you have one question because of that engaging.
Yeah, one of the first algorithms that were shown to be superior on quantum computers is, of course, this Shor's algorithm that can factorize numbers. So at which time do you think that we will be in trouble with cryptography, or will we just create longer and longer keys and outbeat the quantum computers?
So Thomas mentioned Shor's algorithm. I didn't put it up here for the sake of time, but that's a typical problem where you have a very small input and a very complex equation to solve that input, and then a very simple output as well. So the Shor's algorithm, what it does is it takes a product of 2 primes and a long number, and then figures out what are those 2 primes that it was a product of. So it's a process where it's very simple to multiply 2 numbers to get an even larger number, but the reverse process is practically impossible for classical computers, and that lies behind public key encryption and in practice everything you do on the internet that you think is secure. But with a quantum computer, so then also the reverse process of factoring the large integer becomes possible. Assuming that quantum computing development doesn't stop now in a year or 2, we are in trouble already now. Because all the information we are sending now, if it's sensitive enough, someone is storing it for later, waiting for the quantum computers to mature, and then read it. And there's plenty of information that will be interesting even when it's 20 years old or 30 years old or 50 years old. But luckily, we are already transitioning to post-quantum cryptography using or not replacing, but putting an added layer of encryption on top of old encryption algorithms that are supposed to be at least safe even for quantum computers. So there was a mail, I think, last week that Zoom now, in their latest version, starts to encrypt the traffic with quantum safe algorithms. But the problem is there now. And anything you already sent 10 years ago, if you don't want your children to know about it in 10 years, then you're in trouble.
Anyone? Yes.
Yeah, thanks a lot for this interesting and detailed and realistic view. Supposedly we know the number of all problems. What is the fraction of problems we can solve with quantum computing?
No, I don't think that no. It's such a theoretical question, but one cannot give anything more than a very rough estimate. And because we really don't know what quantum computers really can be used for. So far, one has not, or one has discovered a limited amount of these really good quantum algorithms that compared to classical algorithms give a huge speed up. But that doesn't mean that there's not 1,000 more of them around the corner, because one hasn't just looked at it so far. But if one looks at these mathematical complexity classes, so then this the problems that are solvable more efficiently by quantum computers than classical problems. So it's a subset of the entire space. So not all problems can be solved more efficiently with quantum computers. But how large that fraction is, so it just depends on how you draw your Venn diagram.
Thank you. We have a couple of more questions.
Yeah, thanks, Mikael. That was really interesting. I was wondering, you said you only have a very short time until the quantum computer crashes.
Yes.
How long does it then take until you can do the next calculation?
Well, you can start immediately if you just reset the qubits. But the problem with the crash is that you cannot read out quantum states. So when you have the value of the qubit somewhere on this sphere, you cannot just do a checkpoint and then restart the calculation, because if you try to read the state of the qubit, then you either get 0 or 1. So you can never know in what state the qubits are during the calculation. So you have to finish the whole calculation before it's useful, because in the middle, it's just random numbers. So even if you can restart the next calculation immediately, you have to start this from scratch. You cannot continue where you left off. And that's the big problem, and also a difference to classical computing, of course, where you can just checkpoint and then the next day restart, or if the queuing time runs out, then you just save your results so far and continue, but you cannot do that with quantum computers.
Thank you. One more question?
I can be very fast to that. So, as I understand, when you have more qubits in the quantum computer, there is a process, I forgot the name of the process, for preparing for allocating the actual workloads to the qubits. And when you have more qubits, you need more time of this pre-processing to allocate on the qubits. So can you elaborate a bit on that, and how this can be, like this pre-processing time can be an issue when you have more qubits?
Yeah, no, but that's a bit what I alluded to, that there is lots of this. If you do it in a brute force way, then it will become inefficient when you have more qubits. It's the same also with the post-processing. So when you read out the data and want to do some sort of error mitigation or purification of the results. So the brute force methods that work well when you have 50 qubits or something will not work when you have 1,000 qubits. So you need to also improve there, and there, for example, AI methods are expected to be really useful, because then you can cut down on the classical processing time that is necessary. But there was this paper by Google before, and I think that did they use 4 minutes or something of, now I'm going to say the wrong numbers, but the scale will be right. So the actual quantum computing time was 4 minutes, but then the classical processing, pre and post processing, so that was then 50 hours or something. So, and that's just because one hasn't still properly started looking into it. So that's also one field where there's lots of classical software development needed, just because the qubit number is starting to scale up now, and the methods one did, like, okay, we don't need to worry about this now, it works for now. Now it's becoming a bottleneck. So the classical processing needed before you can even start the quantum calculation. Thank you.